By the way, there's events coming up. There's RSA this week. You can go for free. Well, I guess hopefully you went for free today if you were going to go. Okay, I guess this is ending today. This was Free College Day. If you went to that or B-Sides or Hack the Bay, let me know so I can give you extra credit. And there's going to be another hacking club meeting in a couple of weeks on the 17th. So let's see. Should be here. Maybe I have to refresh it. There we are. Yep, on the 17th, there'll be another hacking club. That's also extra credit. It's during finals week on Saturday, so that may possibly limit attendance. I don't know, but they have been getting a reasonable amount of students, and they seem to like it, so we're going to do it again. Dave is willing to do it again, which I appreciate. This is the last lecture for this class. I have another class next week, but I'm just going to answer questions. I'm not going to have any new material. So we'll do Chapter 12, and then I'll show you a brand new project I wrote today in response to the news, which is really pretty exciting. We'll get to that. But first, let's do the chapter from the book, which is here, Chapter 12. All right, so this is covert malware launching. Now, there were some attacks back in the days of Windows XP. There's one called MS Blast that would pop up a box on your screen saying your machine is going to reboot in 2 minutes, and that would be 1 minute and a half, and then 1 minute and a quarter, until it would drive you nuts. And you could just go to Task Manager and find the MS Blast process and terminate it. But a lot of people didn't know how to do that at that time, and so that was the time when it was really easy. But now they make it harder. So they make it so that the malware is not obviously running, and you just can't find the process and tell which process to terminate. So you have launchers. Launchers will start another piece of malware inside it or somewhere and conceal that malicious behavior. So the launchers typically include the malware they're going to launch in a resource section. Now, the resource section is supposed to normally has things like icons and images and stuff, but you can put any kind of data there, and you can put data there that's going to be used to load some stuff in memory and then execute it, make it executable. It may be encrypted or compressed, and so extracting it will do things like find resource, load resource, size of resource. As it, in assembly code, it calls these API calls to connect to the resource section and remove the data from there. One way you do it is by process injection. You might do it by DIL injection or direct injection, and we've certainly done this in the projects where you inject code into a running process by tricking it into loading a malicious DIL, a library. So you do things like virtual alloc-x to allocate space in memory and write process memory to write to it. So DIL injection is the most common way. You inject code that calls load library and forces the DIL to load, and just like the Metasploit malicious DILs we made, the payload may just be in DIL main right away. So as soon as the DIL loads, it automatically runs the payload without requiring a call to any of the functions exported by the DIL. So the launcher wants internet access to down more code, but a process-specific firewall, like the Windows firewall, won't let it do that. The Windows firewall can allow only certain applications to reach the internet. So you just inject malicious code into the Internet Explorer processor. These days, I guess it would be Edge or Firefox or whatever is already there that already has internet access. So the malware code, if you have the launcher malware, it'll go into the memory. It tries to get to the internet by launching a new process, and it's blocked. So it injects into a process like iExplore, and now it can get to the internet. That's the idea. If you add it as a library into another process, then it inherits all the privileges of that process. All right. So here's an example of this. You get your victim process by open process. Then you allocate some memory in the victim process. Then you write into the process memory the malicious code. Then you get a handle, load library, and create a remote thread. So that's how you do it, to run code to launch it in. And here's DIL injection in a debugger view. Here it is open process, virtual allocation, connect a kernel through and load library, and create remote thread. So it'll load it in the library and start running it. So if you find that activity in disassembly, then you can look for strings that may contain the name of the malicious DIL in the victim process. Of course, those might be obfuscated, but maybe they'll just be sitting there. And you can also just put a breakpoint and examine the stack. If they're somehow encrypted, they'll have to eventually decrypt them to use them. So if you put a breakpoint where it's actually trying to pass those things as arguments into the API, they must be decrypted at that point. As we talked about it before, this is often how you overcome obfuscation and encryption, is by just figuring out where the code, the malware has already decrypted it for you and put a breakpoint there. And then, of course, direct injection, like we talked about last time. If you don't want to use a DIL, you could actually inject code directly into the process by modifying the existing code. This is much more customized, requires more skill at assembly coding, so it's harder to write, but it's another way to go, and even sneakier. All right, and then there's process replacement, where you overwrite the memory space of a running object with malicious code. After I learned this technique, I advocated it one time at the college. We had a teacher who wanted to teach an Internet of Things class, and the administration did not schedule it, although they promised to. And so I told him, you could just take a 106 class and replace it with the other class and run it and just tell the students what's going on. But this, of course, is not a perfect thing, because then the students have the wrong class on their transcript and stuff like that. And ultimately, they didn't do it. But I got the idea from this. You take a running process and you just replace it with different code, and now that process does a different thing, but it continues to run under the old user account with the old privileges with the old name. So that's pretty nasty, but it is one way to do it. So you'd replace something like servicehost.exe, which, as you remember, is running a couple of dozen instances in the background, running Windows background services. You can replace one of them with a malicious thing and run it in the background. So what you do is you suspend the state so it stops running, then you can modify it, and then resume execution. That's typically how you do it. I don't know anybody that would try to write to something while it's running. It's probably not even possible. So you use create suspended, and then call the create process. So it looks like this. You create it suspended, and then you create a process. So here you go. Unmap the view, you create a process, then you unmap view of section, virtual allocate memory right into memory, then set thread context, and then resume the thread. So you suspend it while you modify what it contains, and then you resume it. And this, by the way, is common for everything. I was just teaching this at the other college. Remember, you have a multi-processing computer, so it is constantly suspending one process to give time to the next. So this is a built-in function that happens many times every second. Every process is suspended for a while and then resumed later. So that's a normal thing to do. It's just normally done by the operating system, not by the code written by the developer. And so here you go, unmap view. Yeah, same thing. So set thread context. Let's see, anything you say about this? Yeah, we talked about that. Set thread context restores the environment and resumes the thread. All right, let's take a look at a Kahoot. I should have them ready to go here. 12A is here. All right. All right. Oh, all right. All right. Good. All right, may only have one person tonight. We'll carry on. All right, so where do launchers get the code? In the resource section, typically. Good. All right, which technique uses a suspended state? It's process replacement. You suspend it so it stops running, then you change the code, then you resume it. That's how it goes. DIL injections do not need to suspend the process. Those happen while the program is running. All right, which technique requires the most customized code? Yep, that's direct injection. You have to write custom assembly code to stick in for the particular process you're attacking. All right, and what's the most common covert launching technique? Dynamic link library injection, DIL injection, the most common technique. Simplest and easiest. All right, and which process uses find resource? That's the API call to extract information from the resource section of code. All right. Well, I know Lee won. All right. So let's go on. So then there's hooking. We talked a little bit about it last time. I'll talk about it in a bit more detail. So hooks intercept messages intended for applications. And this is an important fact about the Windows operating system and all modern operating systems. They are interrupt driven. They're just sitting there doing nothing when nothing's happening, and then they're waiting for signals that come in from the network or timing on background processes or the user clicking a link or pressing a key press. They get a signal saying, oh, something's happened, you better respond to it. So they're listening for these messages, telling them when it's time to do something, and the hook can intercept those messages and say, oh, before you do that, do something else. Because I might have like a special fancy Bluetooth keyboard or a Bluetooth or some other unusual monitor or something. I say, oh, if you have a signal headed to the monitor, let me check and like tell my special monitor to interpret that signal differently, something like that. So you can put in malicious hooks that will just make sure that this extra code will run whenever a certain message goes by. It might load a DIL. And so normally your user does something like press keys or something. Those send events to the operating system, which go to your application. But if you turn on a hook, you can add a malicious DIL here that's involved. Extra library functions happen on the way to the application. So local hooks manipulate messages designed for an internal process. Remote hooks manipulate messages that go to a different process on the same computer. So high-level remote hooks require the hook is in an exported procedure, and low-level remote hooks require that it's contained in the process that installed the hook. And so this is why there's some malware which infects your the rootkits that infect every process that's launched on the machine. So a connection to the malware is added to every process. And then we have these low-level remote hooks that can run your malware directly inside each process. The other way, it'd have to keep reaching over to another process all the time. Both of them in principle will work. They're just different ways of accomplishing the same thing. And you can make keyloggers out of these. Chemical thing you do, so you use these kind of procedure calls, or these are procedures, keyboard, hooks, and so you might see set Windows hook EX for them. You have type of hook, points to the hook procedure, a handle to the module, and the thread to associate it with. So you can call next hook EX, so it's things you look for here. So I think I've got an example of that coming up. So you could load into all threads, like I said, and that might degrade system performance and might catch an intrusion protection system. Keyloggers do this in order to get all the keystrokes, but other malware might target a single thread. I remember the malware that attacked Target 8 or 10 years ago to steal their credit card numbers was really quite smart. And rather than doing anything sloppy, they actually scanned the memory and carefully found just the credit card numbers and just compressed them and sneaked them out in small packets. So it was careful, not to do something sloppy. Anyway, you can also target a Windows message that's rarely used. There's something called computer-based training, which I think would only be used if you're using your computer for some kind of online test, like certification test or something. I mentioned this before. Windows has a whole bunch of processes running that are almost never used that you probably don't care about. They could be broken, they could be modified, and you wouldn't notice. So here's what's coming up. We're going to load a malicious DIL, and it's going to name it hooklot.dil. We're going to get the address to the malware process. It's going to call next hook.ex and use that CBT message. So here's what it looks like. Your library is named hook.dil. You prepare these for a system call. You push these things onto the stack and then call. So this is going to get the notepad thread, and it's going to set a Windows hook into it. So this will catch key presses typed into Notepad. All right. And then there are detours. There are many, many ways to do everything. This is yet another way to add extra code to Windows programs. So the point is to modify applications. And again, it is as if Microsoft wanted to help malware authors, but it's just because Windows is so big and complicated. There are just so many ways to add extra code to processes because there have been so many versions of Windows and there's so many strange hardware modifications and stuff you make that it just turned out to be useful to have a whole bunch of ways to say, wait, before you do that, go do this other thing. And of course, they can be abused. So you make a detour section in the portable executable, and now you can tell it to detour for certain calls and go to this other code. So here you got a detour section, and then there you got an import name table and such. So setDil is used to point the portable executable to the new import table, and there are other ways to add another detour section, but you end up with text, data, and resource like we're used to seeing, and a detour section, which includes more code that runs in addition to the normal code. And then there's another way to do it. All these do the same thing, asynchronous procedure calls. It turns out every thread has a queue of these things attached to it, which are other things to execute. A thread doesn't just execute one piece of code. It has a queue of various code chunks to run. So they're processed when the thread gets its chance to move. So when you call these things, when it's in an alterable state, like sleeping or waiting for something, then it can run the asynchronous procedure calls. These are things that can be done while the thread is otherwise waiting. So you have kernel mode ones and user mode ones, and you can inject an extra APC in either case. So you queue a user APC and then wait for something. This is the most common wait call. Many threads are usually in the alterable state. Like I say, most of the threads are all waiting. Each one of them, at only one at a time, gets a chance to have some compute cycles. All the rest are waiting. So it's very common that a thread is in the waiting state. And in that time, the asynchronous procedure calls can run. So you got a handle to it, you have function to run, and parameters for it. And it looks like this. As always, you push these things onto the stack, the parameters you're going to need, and then you call queue user APC. This is the way a function call, a single line that would call a function, looks like this in assembly code. You push the parameters on the stack, and then you call the function, which goes and finds them on the stack. All right, and you can do it in kernel space too. And it turns out, now we mentioned before, if rootkits want to run user space code, that's not easy to do, but one way to do it is APC injection. And in the kernel, you call these kernel versions of initialize and insert queue APC. So that's a way you would add a task to be done by userland code in an asynchronous manner. All right. Asynchronous code is strange and confusing. JavaScript always runs this way. I was very baffled when I had to write a Node application for a client, and I couldn't believe it. But one thing about JavaScript and Node.js, which is also JavaScript, is if you write a series of lines, they do not execute in order. Each one of them is treated as an independent job, and they execute in a random order. I couldn't believe it. I was so used to languages like Python and C and every other language where code executes in order. You have to put special tricks in your code to make it actually execute in order in JavaScript. It's all asynchronous, which is mind-bending and strange. And that's what these APCs do. They're asynchronous calls. So let's do the other Kahoot, which should be here, and there it is. My Node application ended up with 8 layers of nested curly braces. I thought the professional developers I was training would notice how crappy my code was and complain, but that did not happen. They didn't seem to regard it as any worse than other people's code. I guess a lot of people, like me, can't figure out a really elegant way to make JavaScript code execute in order. The only way I could do it was by putting each new command in another nested layer of curly braces. There is something called a promise that you're supposed to do, but I couldn't figure out how to make it work. Anyway. All right. All right. Which technique manipulates messages from a process to itself? Yep, those are local hooks from one process to itself. All right, which one will hook all processes? Keyloggers typically will. These other things are just techniques, but keyloggers typically hook all processes in order to catch keystrokes going to all processes. None of the others intrinsically do that. All right, which technique adds a new section to the PE file? The detours. Detour is a new section in the PE file. All right. And if a kernel mode rootkit wants to execute user code, what can it do? It can add it to the APC queue so that it will eventually be executed by that process. And which one only works when threads are in an alterable state? It's the APC injection. You must be in an alterable state to add something to that queue, which is a suspended state. All right. And I think I know who the players are. Lee and Hacker Kitty. Yep. All right.